In section 4.9 here, we're going to talk about polynomial functions and their graphs. So we're going to first identify equations that define polynomial functions. We're going to determine the degree of a polynomial functions, the intercepts of the graph of polynomial functions, and some properties of the graphs of polynomial functions. Okay. So in the first example, we have a silo style tank here, and the volume of this tank is represented by the formula V equals 2.1 r cubed plus 37.7 r squared, where r is the radius. So they want us to first just determine the volume of the tank if the radius is 3 feet. This is just an example of a polynomial function. Polynomial functions are going to have additive terms that have variables with whole number powers. This one's a cubic because it has a highest power of 3. So it's going to plug in some numbers to this function and evaluate it. So let me get it typed in. Our v of our function is 2.1 r to the third plus 37.7 r to the second. And if we want to evaluate this at a radius of 3, then our volume is going to be 396 feet, cubic feet, because it is volume. Okay, so we'll just make our note here that v of 3 is 396 cubic feet. So I'm not going to do much with this example, but it's here to give us an example of a situation in which a cubic polynomial type function might be useful. It would be useful for this type of three-dimensional shape. Okay, now going on. Definition-wise, we've got a table right here talking about a polynomial function. If it's going to have degree 1, it's a linear function. That's an example of a linear. If it's going to have degree 2, it's a quadratic function. That one's a quadratic function. We've talked about linear and quadratic functions a lot in Chapter 1, and then the quadratics in Cluster 1 of Chapter 4. The other types for degree 3, degree 4, and degree 5 would be called cubic, quartic, or quintic, and so on. And then we use the word polynomial to talk about the whole class of functions regardless of what its degree is or what type it might be called specifically. All right, so as we said before, because this function has degree 3, it is a cubic function. Okay, so on to our next page. We're talking specifically in this section about polynomial functions of degree 3 or greater, since the first cluster of Chapter 4 was about the quadratics. So we talked about quadratics extensively already. We want to focus on the other polynomials where they have higher degree. So what is the domain of the cubic function defined by this stuff? So let me go ahead and type this stuff in so we can see what this function looks like. So y equals 2, x to the third minus 8x to the second minus 10x. Okay, so if I look at this cubic function, they're actually having me graph it in just a little bit on letter C. So I'm going to go ahead and use their scaling here. They said an x min of -5, an x max of 8, and a y min of -50, and a y max of 10, and then a y scale of 5. Sure, I can put the scale in. Don't usually use scale, but I can do that. And there's the function. So what the scale does, it just means I don't have to have labeling on every number. It labels them by 5. That's what that y scale 5 means. It means my labeling is by 5. No big. Okay. So that's my picture for this function. And they would like us to discuss the domain first. So the domain is the inputs. And I can see my function takes in a variety of inputs. It takes in negative inputs, it takes in positive inputs, and there's not really any limit to what it can take in. Could I plug in a number less than -5? Of course. So if I name this as f of x, could I figure out what f of -10 was? Sure. It's just really big, and so that's why my scale is not showing that output value. But I can certainly plug in really large negative numbers and really large positive numbers and so on, and I'm going to be able to plug in anything. So the domain for my cubic polynomial is -infinity to infinity. Determine the y-intercept. Okay, the y-intercept is at 0, 0. And I could also do that one algebraically. If I were to plug 0 in for x, I'd have 2 times 0 minus 8 times 0 minus 10 times 0. That's 0 minus 0 minus 0. It's 0. So 0 comma 0 is my y-intercept. Okay. Now we've got our sketch here, and we want to write the equation to determine the x-intercepts. So the equation to determine the x-intercepts would be to take the equation and set it equal to 0. So 0 equals 2x cubed minus 8x squared minus 10x. And now it wants us to use the graph to find those x-intercepts. Okay, so the x-intercepts are going to be at -1, 0, and 0, 0, and 5, 0. So there are 3 of them. When we had a quadratic function, we had the option of having 2. Sometimes they only had 1. Sometimes they had 0. So our quadratics could have up to 2 x-intercepts. Our cubic functions can have up to 3. They could have 1, they could have 2, they could have 3, depending on their shape. They can have up to 3 x-intercepts. This one has 3. Can this be solved using an algebraic approach? Yes. Okay, so hopefully we'll get to do that on the next page. Maybe, do we get to do that same one? No, I don't get to do the same one. So how about we do it? Since the answer was yes, maybe we should do it. Okay, so it says, yes, I could solve these algebraically. So the process is going to involve some factoring. So since the answer is yes, why don't we go ahead and do it? So we're going to start by factoring this. So we're going to have our 0 equals 2x cubed minus 8x squared minus 10x. And what I'm going to do first is a GCF factor. So on this one, the greatest common factor is going to be 2x, since 2 divides into 2, 8, and 10, and they all have at least one x. So we're going to take the 2x out, and that'll leave me with x squared minus 4x minus 5. And then we're going to try to factor this trinomial. The 2x has been taken out, but I have a quadratic trinomial, so I can factor this again using the techniques from earlier in the chapter on factoring. I think it was section 4.5. So we'll be able to break this into something, x times x, because the only way to make an x squared is an x times x. And then I can try to figure out what goes into -5. That's going to add up to -4. So with a -5, I can do 5 and 1. 5 minus 1 would have been positive 4, so almost there. I'm going to want this to be 1 minus 5 to get it to be -4. So I want the 1 to be positive and the 5 to be negative, so that the mixed term in the middle comes out as -4. Okay, so then using the zero product property, the ZPP, we will set each factor that has a variable equal to 0. So in the first one, we'll set 2x equals 0. So divide by 2, divide by 2. That gives us x equals 0. Then in the next one, x plus 1 equals 0. We'll subtract 1 from both sides. That gives us x equals -1. And in the last one, x minus 5 equals 0. We'll add 5 to both sides, and that gives us x equals 5. So our solutions are x equals 0, x equals -1, and x equals 5. And we can see how those give us the x values of the ordered pairs to the x-intercepts. X equals -1, x equals 0, and x equals 5. So -1, 0, 0, 0, and 5, 0. So it is possible to use factoring to solve this one using the algebraic approach. All right. So moving on, we're going to use an algebraic approach, i.e. factoring, to determine the x-intercepts for each of these. Okay. So first of all, we need to GCF factor first wherever possible. And 2 does not go into 5, so I can't pull 2 out of everything, but they have at least an x in common. So I am going to GCF take out the x. So y equals x times 2x squared plus 5x minus 12. Okay, now we're going to trial and error factor this on the side because I don't have just an x squared. I can't break this down directly, but I want to think about 2x squared being 2x times x, and then there's a lot of ways to make 12. So -12 could be made by negative 2 times 6, or vice versa with the negatives. It could be made by negative 3 times 4, or vice versa, and it could be made by negative 1 times 12, or vice versa. So lots of ways to make a negative 12. We're going to take 2 and see if we get there. So I'm going to do 2x and x, and we'll start trying to break this down. Now, to be strategic on this, let me pick the first group first here. So the negative 2 and the positive 6. Now, before I even do anything with this one, I know it's not going to work because there's a GCF here in 2x minus 2. And there's no GCF in 2x squared minus 5x minus 12. I've already taken the x out. 2, 5, 12 have no number in common. So anything with a GCF in it is automatically out. So I know that this is not going to work if I put an even term in with a 2x parentheses. So in either order, that's not going to work. I don't even need to try any further on that one. So we're going to switch it around, and we're going to do a different pairing. So I'm going to do the negative 3 and the 4. I know the 4 cannot go in the same parentheses as the 2 because that would give them a 2 in common. But I could try the negative 3 with the 2 and the 4 with the x. Now let's see if we got there. So we're going to look at our mixed terms. The first one gives us 8x minus 3x. That gives me 5x. So that does it. And so our factoring over here, because the 5x is our goal, right, as our center term, and I got it. So our final factoring over here is x times 2x minus 3 times x plus 4. And that is factored. They didn't ask me to solve or find the x-intercepts. They just said to rewrite it in factored form. Now they want us to verify our results graphically. So to verify my results graphically, I can graph the original 2x cubed plus 5x squared minus 12x. I'll rescale that a little bit. And then I can graph my answer, which is y equals x times 2x minus 3 and x plus 4. And what I'm hoping to see is that the two graphs are identical, that the graph of the factored version lines up exactly on top of the graph of the original, so it shows me that my factored form is identical or equivalent to the original. So it does, and so I know that I have not made any mistakes during my factoring process. Okay, so getting to the next one, I'm not going to be able to factor in part B until I have distributed. So we'll go ahead and do the distribute on this first to see what it is we're trying to factor. So we've got x to the fourth here minus 5x squared plus 4. So this is a trinomial that is quadratic-like. So I'm going to be able to factor it into a quadratic using the property that I know that x to the fourth can be found with x squared times x squared. So I'm going to start my parentheses with x squared times x squared. I want the middle term to be x squared. And if I did it any other way, if I did x to the fourth as x cubed times x, for example, my middle terms would have been an x cubed term and an x term, and they would not have combined to the x squared term. So the only way to add to an x squared term and have an x to the fourth term in the middle is if the two front terms are x squared. Okay, so the two front terms are going to be the same. They're both going to be x squared, and since they're going to be the same, I'd only have to worry about that 4 and breaking that 4 down to make a negative 5. So I could do negative 2 and negative 2, which would get us a negative 4, which is not what we need. Or we could do a negative 1 and a negative 5, which would get, sorry, a negative 1 and a negative 4. Goodness, they have to multiply to 4. Negative 1 times negative 4 multiplies to 4, and then it adds to negative 5. That's what I was thinking of earlier. It adds negative 5, and that pair does it. So we're going to stick this x minus 1 and x minus 4 inside of our parenthesis there. So let me squiggle out the space for the work there. Now, these are quadratic, so I'm going to actually be able to factor this some more. Still, x squared minus 1 is factorable because I know that if I take negative 1, I can multiply 1 times negative 1, and 1 plus 1 is 0, so it's going to add to a middle term of 0. So this first one refactors into x plus 1 times x minus 1, right? 1 times negative 1 is negative 1, and 1 plus negative 1 is 0, so there's 0 in the middle term for x. Same thing happens for this one over here. Because 4 is a perfect square, this is also going to factor into x plus 2 times x minus 2, because 2 times negative 2 is negative 4, and 2 plus negative 2 is 0, so I have 0 as the middle term. So together, those 4 pieces are the factored version of this one. I had to get this all the way factored, so I couldn't stop until every quadratic had been broken up, unless it was not factorable, but I broke it down until it was all the way factored. So this original, hang on, this original function was x squared. I'm even going to do it pre-distribute to make sure I didn't make any mistakes there. Minus 5x, and then plus 4. And then, look at that interesting shape. I have x plus 1, x minus 1, x plus 2, x minus 2, and they are, again, identical, showing us that this is the correct version. This is the correct factored answer. We have no mistakes. This matches the original. All right, one more thing to get factored. Here I only have 2 terms. If I have a trinomial 3 terms, then I can try breaking into 2 parentheses like we did in the first 2. But if I only have 2 terms, unless those 2 terms have no variable in common, if they just have a term and a c term, that I can split into 2 parentheses. But this one's not quadratic, so my first go-to is going to be GCF on that. Okay, so there is certainly a GCF here because there's a lot of x's in common. As a matter of fact, there's 2 and x cubed in common. Okay, so our g of x is going to equal, we're going to take that 2x cubed out, x squared will be left in the first term, and minus 9 will be left in the second term. Now I'm in a situation very similar to the x squared minus 1 and the x squared minus 4, because 9 is a perfect square. I know that 3 times negative 3 is 9, and 3 plus 3 is 0, so I'm going to factor this into x plus 3 and x minus 3. So this one will finish factoring as 2x cubed times x plus 3 times x minus 3. Again, that works because 3 times negative 3 does multiply to negative 9, and if you multiply these all together, the middle 2 terms would be 3x and negative 3x, and those add to 0x in the middle to match the parenthesis there with the b value of 0. Okay, so double checking that we have the correct answer. The original here was 2x to the 5th minus 18x to the 3rd, and then our answer is 2x to the 3rd times x plus 3 times x minus 3, and it matches. Cool shape on that function. It matches so that I can see that my factored version is equivalent to the original function. Okay. And that's what this block right here is saying is maybe not. Oh, we're talking about maxes and mins. Okay, so returning to the original cubic function, we want to talk about the highest point and the lowest point and intervals of increase and decrease. Okay, so let me get that function typed back over here. This was our cubic function minus the 8x squared minus 10x. Okay, so I'm going to zoom in on this a little bit and identify the maximum point and the minimum point. So a quadratic function has a vertex, which is either a maximum or a minimum. Cubic functions may have both a maximum and a minimum, or they might have neither depending on what their shape is. So this particular one has a maximum point at, I'll just make a note of it off to the side. It has a maximum point. Let me pull this down so you can see what I'm writing as well. It has a maximum point at negative 0.523, comma, I didn't leave myself enough room to write, 2.756. Okay, and it has a minimum point at, I'll leave myself a little bit more room to write here, minimum point of 3.189, comma, negative 48.385. Okay, now we want to talk about the intervals of increase or decrease. We did these when we were talking about the quadratics. We're just going to expand upon this into the higher order polynomials. They've drawn two nice graphs for us. My function increases until it hits its maximum. Then it decreases for a chunk. And then it increases again after it hits its minimum up to the rest. So it has two different areas over which it's increasing, going up, goes down for a ways, then goes up again. So there are going to be two places where the function increases. When I do these intervals, these are x-axis intervals, just like they were for the quadratics. When you explain where something is increasing, you talk about it in terms of the x values. So this is going to be from forever. So we're going to be increasing from negative infinity up until this x coordinate, and the maximum x coordinate is negative 0.523. And we're not going to put a bracket on that value to include it, because at that point it's not increasing anymore. It has stopped increasing and it's going to begin to decrease. So we're only going to use parentheses for our intervals of increase to signify that it increases up to there, but not still doing it at that point. Then we can just say the word and, or we can use the union symbol, which is the symbol that stands for and, the other interval. This one is going to begin its increase at this minimum point, which has an x coordinate of 3.189, and it's going to continue increasing infinitely. Okay, so all of that is the increasing set of intervals. Okay, then we're going to get to the decreasing portion, and we're going to decrease for this portion between the maximum and minimum points. We're decreasing just one time, and we start our decrease at negative 0.523, and we finish our decrease when we get to 3.189. Again, parentheses on that, and we're using interval notation to express the locations of where we increase and where we decrease. Okay, next, number 5, use my calculator to draw a bunch of cubics. Be careful of window choices. Okay. I just want to get a sense here for what cubics can look like. I'm going to zoom home first. Y equals x cubed. We saw this one in the last section because it's a power function. And I'm not going to use scale. I'm just going to draw the function. So that's y equals x cubed, approximately. Then we're going to add some more details. What if it was 3x cubed minus x minus 4? Okay, so this one, okay, I'm going to add a teeny tiny bit of details because I want to talk about how many x-intercepts and stuff it has. So I guess I'm going to stick some axes in here. Axes like this. Okay, so this one's got 1x intercept. This one also has 1x intercept. Okay, let's see what other possibilities we can have when we change those values. Let's look at 0.2x cubed minus 2x, and then plus 7. Okay, so give myself a set of axes real quick. This function looks like this. Okay, 2 more to graph. We want now a negative 5x cubed plus 1. Okay. There's our shape for that one. And the last one we want to see is going to have a negative 0.6x cubed plus a 2x squared and then minus a 1. Okay, so let's draw this shape. And oops, there we go, close enough to that shape there. Okay, so I want to, in the next page, generalize a few of the things that we noticed from these graphs. So what are some of the similarities that these graphs all have in common? What about turning points? What about increasing, decreasing intervals? Some of the conclusions we can get. Now, your conclusions might be different than mine. You might have more or less to say depending on what you're observing. What I'm going to note is that there's really two basic shapes. There is the squiggle shape that has all increasing, or it could have been flipped upside down and been all decreasing, depending on if the coefficient was negative or positive. So these two shapes are either all increasing or decreasing. They're not changing. It's not sometimes increasing and sometimes decreasing. It's all one or all of the other. Okay. This shape right here also has no turning points. Okay. This shape right here also has one x-intercept. And all of them have one y-intercept. So that's not even worth mentioning. One y-intercept for all of them. Okay. Um, so I noticed all those things about that shape. And that shape is the shape that we see in part A and part D. In part A, it was the increasing shape. In part D, it was the decreasing shape. Okay. Now, in the other functions, we have some bumps where we're going up, then down, or vice versa. So we have increasing, decreasing, increasing, or decreasing, increasing, decreasing. So we have those shapes. This is the other type of cubic. And you see this type in B and C and E. Okay. So in this shape, they have two turning points. Both of these shapes have two turning points. And one of those is a max and one of those is a min. Okay, so one max and one min. Two turning points, one's a max, one's a min. And so it does change from increasing to increasing, or vice versa from decreasing to increasing to decreasing. So it changes from increasing to decreasing to increasing, or vice versa. So it's not always increasing or always decreasing. It's going to be increasing, decreasing, increasing, or vice versa, decreasing, increasing, decreasing. These ones could have one or three x-intercepts. So parts B and C have one x-intercept, like B or C, or three x-intercepts, like E. Now, it's also possible it could have had two. None of these ones had two. So I'm going to say or two x-intercepts. So what is not possible is more than three. It's also not possible for them to have zero. Note that. Because the tails are going in opposite directions, it's always going to be at least one. So this shape could have one or two or three x-intercepts, depending on what the other values in the equation are. So just some things to notice. There are two basic shapes that a cubic might have. Now we're going to explore some fourth degree, some quartics. We're going to graph them and then do some general summary stuff about the quartics. Okay, so put my Desmos on top this time, and the first one is our power function. We saw this quartic guy in the last section. So the first function is kind of like that parabolic shape with the wide bottom for the quartic. That's my quartic. Okay, now let's add some deets. We got our 3x to the fourth minus x minus 4. Ooh, that's an interesting shape. Okay. Okay, and what else can we get? We'll add or multiply by a negative 2. We'll move in a negative 2x to the second term. We'll add in a 7x term, and we'll subtract off a 4. I gotta zoom out to see this thing. Okay. So this is very similar to part B. It's just kind of flip-flopped, and it's a little more extreme in its dip. So I'm seeing a kind of similar shape here between C and D, right? It's just a little flipped, but the shape is similar. Okay. And then we'll look at a negative 5x to the fourth. And, oh, I got to add the 1. Okay. So this should be a little bit narrower and a little bit taller than the previous one, but kind of the same shape. So really narrow, really flat, something like that. Okay. Again, my picture is not to scale with the original, but you get the idea. And the last one they would like us to take a look at, negative 0.6x to the fourth plus 2x to the third minus x plus 1. And our shape gets even more interesting. Okay. So, all right, there is another shape. Okay, so let me move decimals out of the way. We got to see three different shapes really. So these two are the same shape, just one got flipped upside down and shoved around. Those are mostly the same, they just kind of flip-flopped. Then this one's a distinct shape. It's a different amount of curves or turning points than the other two. Okay, so uh, one of the options is that we can be of that power function shape, right, with that wide bottom. So we could look like this, or we could have been flipped upside down, of course, and we could have been looking like this instead. Okay. So in this case, we would have one turning point possible. And we would have one extrema, which is a general word to use for a max or a min. So one max or min, one extrema. You could also say, I could use the word vertex when I only have one, so I could put the word vertex here. That word's traditionally only used in terms of quadratics. We use extrema a little more broadly, in case you are wondering. But it's one of those things. What else they want us to look about? Comment on turning points, general trends. And then we should note for a general trend that they are going to change from increasing to decreasing or vice versa from decreasing to increasing. So they change from increasing to decreasing or vice versa. Okay, so that is one of our possibilities. Then our shape could look like this, which is my rough estimate of the shape for these two, or it could have gone in the other direction. There's a lot of variety in how this could look. That's another possibility. It's one of those same shapes, but just flipped upside down. And again, the little bump could be larger on the left side or larger on the right side. Either way, left, right side, or left side. Lots of changes, possibilities for ways I could draw this. Now, a lot of the properties of this are going to be very similar. This one still only has one turning point, but it looks different. It still only has one extrema. Now, the extrema and the turning point, that's really the same point I'm talking about. I'm not talking about two different things, but they're calling it a turning point, right? There's only one turning point or one vertex, one max min, okay? One thing that changes the direction. And again, it changes from right here, it is decreasing, decreasing, increasing. So the entire way down to this turning point, it is decreasing. Even that little swish is just a continued decrease, like our cubics up here, where our cubics were always, even with that swish in the middle, always decreasing or always increasing. So it's got a cubic swish in the middle, okay? So this one changes from increasing to decreasing or vice versa. And I'm going to add in the extra detail. This one has a cubic type swish. I don't know what to call it besides a cubic type swish. That extra little wiggle that the cubics have. Okay. And the final type that we saw in part E is, it's often called the W shape. Sometimes they're more symmetric than the one we see. Oops. Sometimes one of the bubbles is bigger than the other, but it's kind of a W type shape, even if it's a lopsided W type shape. And these ones have 3 turning points or 3 extrema. And they change from increasing to decreasing to increasing to decreasing, so they change more often. So it goes increasing, decreasing, increasing, decreasing, or vice versa. Okay, and in terms of x-intercepts, it's possible that these would have anything between 0 and 4 x-intercepts. None of the ones shown in this picture have 4, even this one only has 2. But if you imagine it being pulled down just a little bit, you could hit here and here. So you could go 1, 2, 3, 4. You could have pushed this one up and it could have had 0. You could have pushed this one up so that it just hit 1 time. You could have pushed this one down just a teeny bit so it hit 3 times. So it's possible that these could have 0, 1, 2, 3, or 4 x-intercepts, depending on the shape. They could have up to 4 because they're degree 4. So the highest possible would be 4. Matching with a cubic, the highest possible is 3. So that could have 1 or 2 or 3. This one could have 0, 1, 2, 3, or 4 x-intercepts. One more thing to note about all of these shapes is that the ends of the graph point in the same direction. So they have the same end behavior. The ends point in the same direction. Either both going up or both going down, right? Up, up, down, down, up, up, down, 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 up, up. And back over here to our cubics, the ends point in opposite directions. Right? Down, up, down, and so on. Right? And that's all.